Hi there, in this video I have a very special treat on the repair bench, an advanced DMM2 multimeter in mint condition with Nixie tubes as display. It belongs to one of my patrons, Dave, who asked me if I could have a look as it never worked for him. I connected it to mains through my current limiting light bulb contraption, made sure the power switch on the back was in the on position and then turned the power on. Nothing is happening on the DMM2, but at least the dark light bulb means there's also no major short circuit, which is good. Of course the DMM2 could have wires broken or fuses blown to explain why nothing is happening, so I inserted my power monitor into the mains feed. Ignore the accumulated watt-hour readings since I did not bother to reset the monitor. Turning on the power to the DMM2, and it's clear that something is drawing about 4 to 5 watts. Putting the monitor to the more sensitive ×10 setting, and there is a current of 16 milliamps. We are in the ×10, don't forget. So the DMM2 is not totally dead. On the rear, the DMM2 has a DC in socket, and I temporarily poked 2 wires into the socket to my bench power supply and selected DC on the switch. Turning my bench power supply on, and yes, something is happening on the display. That looks promising. It draws just shy of 270 milliamps at 16 volts DC and feeding some 25, 50, 75 and so on DC millivolts into the meter in the 200 millivolt range shows that it seems to work, sort of. Clearly the digit in the middle is missing, and of course the AC power seems to have a problem too. Time to open it up. It follows the usual design that 2 shells forming the body are held together by long screws through the feed. Once these are out, the top shell can be lifted off, revealing the backside of a PCB that has 2 distinct areas. I suspect the area on the left is clear of the solder stop mask because it's the input selector and deals with very high and very low voltages and high ohms. With the handle removed, it's then possible to lift the whole inside as one compact unit from the enclosure. The whole construction is 2 main PCBs folded so that the component sides face each other on the inside. I spot a fuse, and since it's now easily accessible, it can't hurt to test it. All fine as expected. The front panel is not really attached and only held by its wires to the input connectors. Not great. To do any fault finding, the 2 PCB boards have to be separated. 3 screws on the bottom have to be removed, then the hole has to be put back in the normal orientation and another 3 screws have to be removed from the top, one of which is hidden under a tangle of wires on the left. Then the whole thing unfolds with the 2 PCBs still connected and functional through countless of wires. Okay, it does offer access to most things, but it's the most fragile arrangement and cables can and did snap off during my work, even though I was very careful. It did not help that I had to repeat this assembly-disassembly process about 20 times over the course of this video, because every time I thought I was done and put it back together, only to discover that something else broke. To give you an idea of what makes a DMM2, this is the top board. That means in normal operation it is upside down, so the components hang downwards. It contains the 5 range switches. In this picture they are from left to right for the 2000, 200, 20, 2 and 0.2 ranges. Behind the range switches is part of the input attenuation. The round black things are some of the calibration potentiometers. The rest of this board is the power supply. You can see the mains transformer and the big smoothing cap. This is the lower board, but from the rear. The Nixies would be on the upper right. On the upper left are the function switches for volts, ohms and so on. Almost on the middle there's another PCB that stands vertically on the lower board. This is the AC to DC converter. On the right are 2 dual inline ICs. The one with the golden top is a custom developed chip. The manual calls it LSI, Large Scale Integrated Circuit. It contains the whole digital part of this meter, except for the other dual inline chip higher up, which is a simple BCT to decimal decoder. A quick rundown how this meter works. In essence, it's quite typical of digital multimeters. There is a front part that produces a DC voltage either directly in DC volts or, when in resistance mode, by running a constant current through the to-be measured resistance to measure the voltage drop, or in current mode by running the to-be measured current through a known resistor and again measure the voltage drop. For measuring AC, there is an AC to DC converter that can be looped in. Next, you have this integrating capacitor, which is charged up to a known voltage. The capacitor is now discharged for a fixed period of time at a current proportional to the measured input voltage. Then a counter is started and the capacitor is recharged to its previous level. When that is reached, the counter is stopped and displayed. If the input voltage was very small, the capacitor got discharged with only a small current, so it takes very little time to get back to the original value. If it was a large input voltage, the capacitor got discharged by a large current and therefore recharge takes much longer and the counter reaches a higher value. All this would require quite a number of digital chips, but as you have seen, the whole digital part is all in that LSI chip. Counter, latch store and all the other circuits that help with sequencing the complex analog to digital conversion. If that chip's dead, you are basically out of luck as the chip isn't available anymore. Since the display worked, sort of, when powered in DC, in this DMM2 the fault is elsewhere. So I plugged the AC line cord back in and powered the meter. No display, but I could measure the AC voltage on the primary of the transformer, which explains the power draw I saw earlier. The problem must be on the secondary side. It might be useful to have a quick glance at the schematic. The power supply is actually rather complex. We have the usual mains transformer followed by the rectifier and a smoothing cap to convert it to DC. But since the meter can be powered from AC mains or from an external DC source, what happens next is that the DC from either input is fed into a regulator made of TR36, TR37 as the power transistor, and the Z diode D29. A bit unusual to have an NPN power transistor on the negative side, but why not? The regulator is set to produce 9.5 volts, whatever the input, which then feeds an oscillator producing a high frequency AC going to another transformer. On the secondary of that transformer are taps that create the rectified DC rails for the actual meter circuit, using plus 17 volts, minus 12 volts, plus 5 volts and plus 190 volts for the Nixies. Interestingly, there is no regulation on any of these rails. It all relies on that the input to the oscillator is regulated and the oscillator frequency is constant. There is an additional circuit that takes the AC from the mains transformer and converts the mains frequency into pulses to sync the analog to digital conversion. Obviously, that part does nothing when running on DC, but when running from AC, it makes sure that the integration period is synced to mains, which is a standard way of reducing the effect of mains noise in the measurements. I am measuring 15.5 volts coming from the secondary of the mains transformer, so the transformer itself is working fine. But there is nothing on the output of the regulator. There should be 9.5 volts here. By the way, the strange thing right above the red probe is the second transformer producing all the voltage rails. With the power off, I traced continuity between the secondary of the transformer and the positive connection of the smoothing cap. And for either part of the secondary, that gives the usual diode junction through the rectifier, as you would expect, so all is fine. Now for the negative side of the smoothing cap, which means I have to swap leads of the multimeter as the rectifier diodes are now in the other direction, but nothing. That's interesting. This could be caused by either a half-broken rectifier or the AC-DC switch. The switch is way easier to access. And sure enough, there is no connection to the rectifier in AC mode. The switch is the problem. And after giving the switch a good douse with contact cleaner and operating it for some time, the contact problem is fixed. Apologies for partly obscuring the view. I did not video it, but the AC power works now just fine. On to the next problem, the missing digit. The fact that the other two digits work means the problem is either a broken Nixie or some issue in the multiplexer. As you can see, all digits are connected in parallel from the decoder chip. If you are not familiar with Nixies, the pins in each tube illuminate exactly one number. So for example, the number 3 or 6. The numbers are stacked one behind the other. This is very different from a 7-segment display where a combination of LEDs form the complete number. The anodes are used to determine which tube is lit. The LSI chip, which is not on this schematic, puts the binary coded digits or BCD codes for each digit out one by one, which are then decoded and applied to all tubes at the same time in parallel. In sync with that, the LSI chip drives the P and Q signals, which basically count continuously 0, 1, 2, 3 in binary. Transistor TR28 gets the Q signal and inverts it, which is column A. That column A drives transistor TR29, which also inverts it, in column B, which is therefore doubly inverted and back to Q. Exactly the same happens with TR30 and TR31 and the P signal, which produces columns C and D. In the end, you have this table here, where the 4 states produced by 2 inputs, P and Q, are now patterns of 4 bits, A to D. Each of the anode drivers now decodes 2 bits in an AND gate formed by 2 diodes. So for example, the first digit remains dark until its 2 diodes are both pulled down by the B and C signals, which then causes a quick firing pulse to the Nixie through the capacitor. Since the diodes for each anode driver decode another pair of the A to D signals, they each activate at a different time in the 4-digit sequence, exactly when their specific BCD signal with the right number for that digit is sent out. It was easy to find that the signal D was no longer working because transistor TR31, a BSX20, was nearly dead. That transistor is just a standard NPN switching transistor, not particularly stressed in this application, and I replaced it with a jelly bean equivalent. With nearly dead, this is what my component tester had to say about it once it was removed. And here's the replacement, easy to spot. One quick sidetrack, before I replaced the bad transistor TR31, the DMM2 was running for an hour or so, and it so happened that I just received the top-down thermal camera TS001 for review. The DMM2 made a convenient target while I was playing with the thermal camera. Later, after I found and fixed the problem with TR31, I reviewed the thermal images to see if there was anything interesting to see, and I think yes. The 4 transistors decoding P and Q and producing the A to D signals are all doing exactly the same stuff, yet TR31, which I marked with a white circle, is definitely colder than the other 3. I find that interesting because tradition has it to look for hotspots with thermal cameras, but sometimes an unusually cold spot may be just as significant when troubleshooting. By the way, that bright target at the bottom is the custom LSI chip mentioned earlier. As those are unobtainable these days, let's hope this one keeps working. As I hoped, the replacement of TR31 brought the middle digit to life. There was nothing wrong with the tube itself. Running some tests with the Fluke 77 in parallel with the DMM2 in the 2 volts DC mode showed that the meter was reasonably accurate. I increased the voltage at the input, and when I crossed over the 1 volt boundary, another problem was revealed. The DMM2 is supposed to show up to 1999 on its display. Here we should see 1.008, but it just shows 008. This means the leading 1 digit is not working. This is actually not a proper Nixie tube, but since it only has to show 1 or nothing, it's like a longish neon that looks like the number 1 when lit. Back to the schematics of the display. The BCT to decimal decoder is IC4, another of those unobtainable chips. It's a CUL960. In a crunch you could replace it with a type still available, but need to do some rewiring. I marked which outputs corresponds to each digit. For example, the most left one in this schematic is active when a 0 is displayed, the most right one when a 9 is displayed. which output drives what Nixie number is needed when trying to make sense of the confusing number of indicators on the left. But making sense is relative because there is some weirdness. If you follow the lines from the decoder, the number 1 is connected to ILP4, so that's neon should light when numbers between 1000 and 1999 are shown. So far so good, but I have no idea why there is an ILP9 neon that lights when the highest digit is 0. It is either not there or at least not shown to the user. There is ILP5, which is apparently not a neon but a light bulb and responsible for the overload indication. That one is connected to the number 2, which makes sense. If the display rolls from 1999 to 2XXX, it should come on. I have no idea what's the purpose of ILP8. That neon is in series with all 3 and would therefore light if the highest digit is either a 0, 1 or 2. It might be mounted invisibly just to reduce the voltage so the brightness of the other neons match the Nixies. There's actually one more strange display thing, this piece of circuit, which drives a polarity light. The DMM2 can't measure negative voltages. If you do, this light tells you to reverse polarity. Now, since I already measured TR28 to TR31 to find and replace the bad TR31, I knew that these 4 were okay. That left TR32 as the prime suspect, why the leading 1 digit was not working, and a quick test checking the base emitter and base collector diodes confirmed that. After extracting TR32, the component tester only recognized this transistor as a capacitor, so yeah, definitely dead. That transistor is an 2N5400, and since it drives the Nixies, it handles relatively high voltages. It was still available, relatively affordable as new old stock, so I choose to replace it with a new one of the same type. Turning the DMM2 on did not seem to have done anything, until I remembered that it would only trigger if the display was trying to show a leading 1. So, quickly applying 1 volt. And the display just shows 999. Oh, the suspense. I need more volts, quickly. Finally, yes, it works. I have the leading 1. I have not shown yet how the whole display section looks behind the front plate. We have the 3 Nixie tubes, and on the left the long neon is the digit 1. Although it looks smaller than the rest of the display, the length of the glowing part inside is matching the way the real Nixies show 1, so this is obviously part of a set and not just a longish but standard neon. The 2 smaller ones on the left are for polarity and overload. If you recall from the schematic, they are shown as light bulbs, but these look very much like neons to me. The top one indicates reverse polarity and the lower one indicates overload. This is how this works. For example, in the 2 volt range. If the voltage exceeds 1.999, the OL light comes on and the leading 1 goes off. The rest of the display still shows digits based on whatever the counter happened to be. You have to get used to first check OL. If OL is on, ignore the rest. If I now reverse the polarity at the input, the displayed voltage kind of drains away, but only on the display. I have not reduced the voltage, it's still 1.993, I simply swapped the polarity. I can now either swap the leads or press the minus button, which swaps them internally, and the display is back. Notice that the only indication that you are now seeing a negative voltage is that the minus button instead of the plus button is pressed. This is easily overlooked. Coming from modern digital meters that simply show a minus sign automatically, this behavior of the DMM2 is definitely another thing you have to get used to. So, now that everything is working, it's time to do a proper calibration, which, according to the service manual, starts by adjusting the regulator in the power supply to provide 9.5 volts plus minus 2%. Next is to set the DC null in the 200 mV range with shortened input. This pot can also be reached from the outside and can be used to do what modern meters call rel, for example to null the lead resistance when measuring resistance. Of course, you have to readjust afterwards. The problem here is that with the meter open, the location of the pot forces me to hover with my fingers over the power supply while adjusting, That is not nice. Not only is mains voltage close by on the switch contacts in the back, there is also 190 volts for the Nixies on both boards. Anyway, with the meter flapping between 0 and 1 at the least significant 100 microvolt digit, I think that's good enough. Next is applying 1.999 volts and adjust another trim pot at an equally inconvenient dangerous place while the meter is open. Again, the reason for the location is that this pot is also accessible from the outside and kind of the master calibration pot. I declare that one also good enough. Next is to apply 199 millivolts and adjust the reading. Sorry, that trim pot is on the power supply board on the right and unfortunately not in view. Then one must adjust the resistance ranges, starting with a 2 meg range and going down to 2K. I show this part much accelerated as it's actually quite cumbersome, because you need of course matching reference resistors like 1.999 meg, 199.9K and so on, which means you have to use resistor decades to dial those unusual values in. This is followed by adjusting the 200 mV AC range with a 199 mV AC signal at 800 Hz. Actually, the step before that was shortening the input and setting AC 200 mV to 0. I did not show that because it was already set. Now for the same but at 1.999 volts. I think this is good enough. Actually, there are 3 more steps to adjust AC at 20 kHz, which I did but skip here. Basically, I thought I was done and did what I foolishly thought was final assembly. But of course, now the meter did not measure anything anymore. So out of the box it came again, and yes, another broken wire, because this whole thing is so fragile and really doesn't like to be handled. For such cases, it's a good rule to take many photos from all angles before starting with any work. This is essential in finding where the wires should be connected to. Anyway, I put it back together and it all worked. Hooray! Until the next day, when I found that the AC range had stopped working and was now just displaying 0. Something new had failed in the DMM2, but what? If you enjoy my videos, don't forget to like and subscribe. There are many more projects, repairs and reviews coming, including the next part of this video. And it would be great if you decided supporting this channel by becoming a Patreon. Thanks for watching.